now we'll have a presentation by Samuel Yvon on Gambit on bare metal.
Yes.
Something that actually has been part of the motivation for Gambit about 30 years ago, and that has finally happened this year. This idea of basically being in control of everything, including the very lowest level of the machine, and now it's reality. So let's hear your presentation.
So can we actually write an OS in Gambit now?
We'll see.
All right. So hi everyone. I'm Samuel. So I'm going to be showing you today what I worked on last summer, and as you could probably guess from at this point, it's Gambit on bare metal. So you might be wondering exactly what Gambit on bare metal means. So without further ado, nope. There you go. So this is literally Gambit running on an old Pentium 3 machine without an underlying operating system, or more without a conventional underlying operating system. It runs the full Gambit. Everything that Gambit does can be done on this machine, besides some I/O function, as I'll be detailing later. So you might be wondering how and why we've done this, and I'll be explaining in this presentation the objectives that we had in mind while building the system, and exactly what has been done. So I'll start with what has been done right away. So this is basically a minimal x86 operating system that's designed solely to run the Gambit compiler. So we call this operating system Mimosa, so this is why there's a little logo there. So I'll be referring to the system as Mimosa. So if you hear me talking about mimosas, it's not over, it's just that's the name of the operating system. It's not break time. So this is an x86 32-bit operating system. It contains a driver for IDE drives, serial communication ports, and PS2 interface, so it supports both mouse and keyboard through PS2. In terms of file system, it has a virtual file system implementation to allow mounting ports as devices or other exotic ideas like that, and it supports the VFAT file system, so this is FAT32 with the long file name extensions. It also has supports for multi-threading and all the basic synchronization primitives, so it can run multiple instances of Gambit at once if you are a little bit courageous. So I'll talk a bit more about the motivation. So the idea is that having Gambit running on without an underlying operating system is that it offers little to no overhead with the generated code of Gambit and Gambit itself. So this allows us to evaluate the performance of the generated code and not the generated code and the machine running under it. So it's we basically reduce the random variables that can occur while we benchmark Gambit. The other idea is that it offers a view into kernel development with higher level languages. So the main idea is that we want to build a Gambit scheme implementation of an operating system kernel, and having a base in C allows us to compare many things that will occur. So basically we can compare the human effort required in C versus scheme, we can compare the performance, we can compare the expressiveness of operating system constructs that we can find in an operating system in C versus in scheme. So we basically have a better idea of the effort required. The other idea is that having an operating system in a high-level language like Scheme, and currently this setup, allows us to build drivers in Scheme and hot swap them basically as we develop the operating system while we are using the operating system. So since there is a base in C and the rest can be done in Gambit Scheme, we can load drivers, run them. If they don't work, we go back to the editing board on the computer without ever rebooting, and we continue developing the driver. Obviously, there is some little issues that we can encounter, mainly when we use access to the devices, especially network. Yes?
That's a little basic. If your driver crashes, it's very likely that you crash very hard.
Well, there are some problems like that. If you run, for instance, a network driver and it crashes in the middle, we probably won't be able to restore everything like it was. But the main idea is that since the IDE driver is running in C and somewhat stable, if there is a big crash, the system can be reloaded to that state without losing too much information. So I'll be explaining the structure of the operating system. So right now, the BIOS loads the boot code, which is basically a standard bootloader. Then that boot code will start a scheduler, and that scheduler will have the task of starting Gambit. So you might be wondering, why do we need a scheduler if Gambit basically has full control over the system? And the idea is that some drivers will require long-running tasks in the background, and we can support those tasks with the scheduler. So for instance, the IDE drivers does some block caching, and in order to flush those blocks periodically if there are still references, but we don't want data loss, for instance, so the scheduler can run those tasks. But Gambit can also take control of the scheduling and run only Gambit threads instead of running OS threads. And the driver block is basically all the drivers that are implemented. And the idea is that Gambit will call those drivers when required, when you want to do I/O stuff. So all the access to files is done through the C interface. There is no ELF loader currently in the operating system, so there are some challenges with how the Gambit compiler has been loaded in the system. So I'll talk about that later, and also why the driver interface provides little to no overhead between Gambit calls and basically the operating system. So this is a little excerpt of the code. So basically it shows that the Gambit thread is running in a high priority. That means that unless Gambit is waiting on the I/O task, nothing else is taking Gambit over. So basically, when you run a task in Gambit scheme, which is basically the OS at this point, nothing else will run unless Gambit is either waiting for resources that are not free, or yeah, that's pretty much it. So, like I mentioned, the system is tuned to Gambit and not the opposite. So, basically, Gambit has the control over the system. Since the kernel is not mapping Gambit in the user space, it's basically all in kernel space. So this is what allows us to build some parts of the operating system in Scheme and load them in memory and then stop them without having to necessarily restart everything. When Gambit runs, like I mentioned, because of the high priority thread, no other tasks are allowed running unless it's waiting, of course. And the driver part that I was talking about with no system call, it's because since there's no ELF loader, because it's too much time and effort for no real benefit for our case, the libc is implemented as a function table that is mapped into memory that Gambit's load. And all the functions that are required by Gambit are simply called as C function through the libc interface. So this allows us to run operating system function and services without necessarily doing some system calls that would potentially take more time. So it's directly the functions that are called like a normal function call. Yes.
I mean, your point with the libc is just that there is no operating system, right? So you just
Yes.
have like super simple, like just to drive Gambit.
Yeah, so basically Gambit does not have to do some system calls or anything. Since Gambit is pretty much the system at this point, it just does normal function call. But to avoid the problem of having no ELF loader, I don't know if you're familiar with all the technicalities, but since there's no virtual memory, there's a lot of consideration into where we load Gambit into memory and how the functions are coded. So this is basically our solution to that, is basically to have a function table where Gambit is compiled with the address in compile time, and it can load the functions. So, like I mentioned, the kernel has the ability to run interpreted scheme code through the Gambit compiler that has been started up. It can run compiled x86 code with the asterisk that the addresses have to be known ahead of time since there's no loader. And it can compile and run scheme code, as I'll be demonstrating later. So, there are some perspectives for the scheme version. So the idea is to avoid some of the complications that are brought up by C, and we want to still have the convenience of using C, and try to minimize the C issues. So using pointers and memory allocation can caused a lot of problems during the development of the operating system. And the idea is to find a way to maybe get the best of both worlds using Scheme and as little C or assembler as possible. The imperative style of programming is sometimes appropriate because sometimes you have to interface with devices that expect sequential operation. And while it is definitely possible to do those operations in functional style, we want to avoid losing expressiveness, and this is where Scheme allows us to mix a bit of both of the programming style to do sequential separation without losing the expressiveness of sequence structs or things like that. So there are many challenges for the scheme version of the operating system. For instance, managing garbage collection will be a bit of a tricky part. And there's also a way to build a convenient access to memory map resources, some CPU instructions like IO port access, and other physical hardware that rely on IO port access or memory map structures or many other communication methods. So many issues were encountered during the development of this project. Most of the development was done on an emulator, and when we tried to run it on real hardware, we encountered a lot of issues because emulating devices works perfectly because devices are basically always working. But when you put the code on a real machine, you encounter problems with the fact that components don't necessarily work exactly as they should. Sometimes it's programming error, sometimes it's delays, sometimes it's a bunch of reasons. We are stuck with whole hardware support because implementing drivers for modern hardware is a lot of work. A lot has been done to how you communicate with those modern devices. So, for instance, for the reading of the IDE drives, only the sorry.
USB is crazy.
Yeah, USB is a ton of work.
It's crazy.
We wanted to have USB support to boot from USB drives and load Gambit because we can boot from USB, but we can't load Gambit from it. And yeah, I think the USB is too much work for.
Even USB 1, not XH.
Yeah, any
USB 1.
yeah, just USB. Yeah, it's a lot of work. But the bad part is that the BIOS has a way to access those devices since we can boot from them. And we tried to do a BIOS foreign function interface, and that was also a lot of work. So we can't really use the BIOS services for that. So just implementing the USB was out of the question. Even just using SATA drives, the SATA protocol is way more complicated than the IDE PIO mode. And we don't have networking support as of yet, but we're trying to do a port of the H3 library that I'm not too familiar with, but we could port that in Gambit scheme, and we have a TCP stack running in scheme in the operating system. Another big challenge is that we have a very deprecated compiler toolchain. So we use a G++ version 3.4 right now that we have to run on a virtual machine to be able to use. And there's an awkward mix of C++ and C in the system from legacy code and the code that I was writing. So this is another area where we could improve a lot, but there are plans to smooth out those issues.
Yeah, even the latest Raspberry Pi 4 hasn't managed to get USB right.
Yeah, so
Yeah.
we're not going to hope for that. Yes.
How do you handle interrupts when there is a time constraint versus a DC? Many device drivers require you to reply within some time, some deadline before.
Well, since the driver, we don't have that many drivers yet, and we didn't encounter that problem. We tried to get a mutually exclusive set of interrupts that we have to handle. So right now, I don't know them by heart, but for the mouse and keyboard, we're pretty much good. We have the RTC clock that use some, or just the clock mechanisms, but we don't have any clash of multiple interrupts. Maybe beside the COM port that can have multiple interrupts for multiple COM ports, but we only use one COM port. So they all work, but only one is used. So we don't have those problems yet.
And but just GCC 3.4, how there?
Sorry?
How did you get into 3.4?
Well, so when I started the project, I had the code base from Mark that dated from 2001. And the only way to compile it was to start an old Ubuntu VM with a compiler in there. So, so this is the only way we have to build the system now. But it runs with the latest GCC. The problem is that there's probably a bug somewhere or an instruction that doesn't exist, so everything is super slow. So it runs with some tweaking and some removing some of the code, but it compiles and runs in the latest compiler. It's just unusable. So it more or less compiles and runs. But there is a bit of, we have plans and ideas how to fix most of these issues. So we try to do multiple, we have few objectives. So right now the benchmarking capabilities are not really, they're pretty manual. So right now we want to work on the serial to TCP bridge, since we have a serial converter to network, and then we want to access through the network to the serial to the computer. We also would like more drivers. We tried to take some USB drivers from other places, migrate them to the systems, proved too complex. SATA driver is not unattainable, so we could have that. And if we could have the BIOS foreign function interface, that would speed things up a lot. And right now, we want the other objective that we're trying is to have a scheme implementation of a boot sector, of a basic kernel, basic ways to access computer operating system primitives and CPU instructions and things like that. Yes?
Could you leverage code written for, say, unikernels in OCaml or Haskell or Common Lisp or
Not
whatever?
too. I don't know too much about these constructs, so maybe, but I don't know exactly. No, maybe Mark could help.
I don't know if they would be easy to convert.
Maybe not for Haskell, but like the semantics of OCaml and Scheme are pretty much compatible, so you might be able to leverage a lot of the logic from the OCaml.
I would say that a lot of the work has gone into figuring out exactly what kind of messages you have to send the hardware to get the proper responses,
Yes.
and the actual sequences are easy once you know them.
Yes.
And so converting these sequences to scheme should not be the hard part. Of course, if we're talking about USB or something like that, then it's a big piece of code. But for the more basic kind of interfaces to the peripherals, that should be easy to take the C code and convert it into scheme.
Yep. And the idea is not necessarily to implement a fully functional operating system. At the end of the day, it's to see what benefits can be, what benefits can we have from a kernel written in a higher level language, using garbage collection, for instance, or just without having to deal with all those pointers and all the memory allocation you have to do manually. And really, the drivers would be useful to test on more modern hardware, because right now we're really stuck to an old Pentium 3 machine, and it's not necessarily the fastest machine. So for benchmarking, it isn't necessarily you can't compare it with anything. You have to just compare it on itself and things like that. So conclusion. So we're still very far, but we're closer than ever to Gambit scheme kernel. We have found that some constructs and many low-level routine can be done in scheme without loss of expressiveness. And if you want to toy with the code, it should be available soon in GitHub. And I will now do a little demonstration of the system itself.
That was fast.
Well, it's all in a simulator, so
But still, it boots almost instantaneously on real hardware.
there's not much to load either. That's the. I mean, it loads Gambit, and that's it.
So what do you use for the windowing system here?
This is
terminal serial emulator.
well, it's all built in the operating system,
Yeah,
so there is a VGA
all
driver.
that you see is really done by the operating system. So the windowing system is not a real windowing system, so you can't move the windows around, but still it draws everything that you see on the screen here.
And you,
Full screen, so also the stuff to the right.
yes, the
Oh,
stuff to
everything.
the right is a debugging console, if you will, so it shows some debugging output from the drivers themselves.
Wow. Wait, so this is BIOS, based on BIOS API, not UE5, but BIOS, right?
Yes.
Got it.
Well, this is yeah. Mathieu, you had a question.
It was for Mr. Vizo. When do you think to put Gerbil on Gambit on Mimosa?
Tuesday?
That's very cool. Possibly tonight. Where's the pencil?
So you can load scheme files and execute them without a problem. It basically is the Gambit runtime and everything. You can also load longer scripts that will take a while.
Do you have any job control?
Sorry?
Do you have any job control?
Well, yes, but since right now in that mode, Gambit is the only thing. If it fails, we can just kill it and that's it. But then we have to reboot because Gambit will not restart by itself. But it's not. It's done. It's just not implemented in the sense that all the framework and all the
No, but can you like Control Z?
you can control C.
Wait, how do you do malloc?
That's a good question. Well, Basically,
Actually, how do you do malloc?
Do you do it?
yeah, well, that's the other good question. So we try to do a malloc, and it's not that it's especially hard since we have access to all the memory, but it's not really done right now. So we just have a block of memory, and we write, and we never claim anything back. And so basically it will run out of memory eventually right now, but it's
Not like we have to go free.
yeah, it's the best kind of malloc.
But it's not.
like the old day of list machines.
Yeah.
But remember that Gambit is managing its own memory, so it did get some of the M sections with malloc, but once it gets them, it just keeps garbage collecting within those M sections, so it's still okay.
Yeah, there basically is a stack for the system itself, for the drivers. There's a stack for Gambit, and there's a heap for each one of those, but the kernel heap is never cleaned up. So yes, it will eventually run out of memory. So if you don't want to wait for Fibonacci scheme to run, you can compile and run it. And you'll see that it's much faster, so 0.02 second on the real time instead of 10 seconds. And this is all done on the machine, so it will compile the code, which I can show.
So this is actually the x86 backend that was just described, running on directly on the hardware. So it generated the code dynamically and ran it, and it's much faster.
So we can also access some CPU primitives. So right now we'll read the RTC clock. Is that this one? Yes.
Yep.
So we can read the RTC buffers from scheme using in and out assembly instructions. And I think that's all. This one. So this is the nope.
It's the ISM.
There you go. So this is the So this is the example from earlier where it's accessing the nth element from the list from the scheme representation in assembly running on the Gambit operating system.
Any chance of running Emacs on Scheme?
So that's a very good question,
Yes.
and the guy behind you is working on it.
Okay.
Not by running Emacs, but basically rewriting Emacs,
Yes,
a tiny version of
that might
Emacs.
be what it takes.
Because the terminal here responds to all the escape sequences and all that. So it's an afternoon exercise to do the rest.
Has anyone managed to get rid of all the dynamic variables yet in Emacs?
Yep. So that's pretty much it. If you guys want to try anything, I guess I could run code. But
Do you have an image? You're going to put it on GitHub.
well, I would want to put it on GitHub, but that's not. I don't have control over the repository. So. But yes, there is images.
It's planned. It's just time has been very lacking these past few days, but that's the plan. Maybe we'll do it tomorrow or something like that.
So you're going to start your company, call it Microsoft, and then
Yeah.
sell it.
Micro scheme or something.
So,
Microsoft.
I want off of the shares.
Don't get
So-
mixed up with
I did it right.
Microsoft.
what I find interesting, of course, there are many cool things in this, but it's the prospect of actually writing parts of the operating system in Scheme, but by using the interpreter. So interactively, just trying things out, figuring out how to read the real-time clock, for example.
Yes,
Here it's
yes.
done. But you do it interactively, and instead of recompiling your kernel, rebooting your machine, and going through all of this this process, you can do it interactively. And maybe it'll fail.
Yeah.
Maybe it's just like too much, and the system will be too unstable or something like that.
Maybe
But
just impossible.
it's an interesting experiment to try to see how far you can actually go by doing this.
Can't you forget about writing your own device drivers? Start on top of them. Because device drivers you can spend a lot of time on them.
We could port some device drivers. The problem is that the design is not exactly perfect, so there are some drivers that would be hard to port. first of all, there's a compiler issue to fix because we don't know what compiler version the devices or the drivers are going to use. We don't know what features they're going to use. So right now with G++ 3.4, it's a little bit iffy. But technically, it would be possible to port some device drivers. But sometimes they're very. We can't just take the device driver for whatever from the Linux code because there's too many branching, and we tried some things, but that didn't really work out.
We want to get rid of all of the C code as much as
The C++.
possible.
Oh yeah, at the end of the day, yes.
So reusing existing device drivers sort of
Takes away from it.
we lose sort of the coolness of doing this. Of course, we won't have USB drivers or things like that unless we can find a way to do that in Scheme. But in a certain sense, we're not, after replacing Linux or Windows or whatever, we just want a nice environment to play around with hardware.
But I mean, with bottom half, you're just usually dealing with vendor binaries and numbers and sequences that don't really have any logic that you can control. So it's force feeding it. Scheme or C doesn't seem to do a lot of
You mean for
just
some?
device drivers in general. Blobs
What's your point?
Oh, at the bottom half is you're usually just dealing with a lot of sequences of blobs and other magical numbers that you're just feeding in, and there's not a lot of logic around. How does this work? What does that do? The vendors
Perhaps,
really do
yeah.
it. So it seems like doing it in either language would.
Of course, I'm hoping that this will attract sort of hackers to try this out and to actually contribute Scheme code to this, and maybe if there's a kind of a community that can be built around that, perhaps attracted by the coolness of it, then maybe the device drivers will write themselves.
Yes, and how much faster would the Fibonacci benchmark be if you run it, for example, on Linux? So you do the exact same thing except on bare metal?
Well, you would have to compare machine to machine.
Yeah, but on the same one. If you just plug in.
You could check that out. We never tried those.
Well, maybe you can do it offline, but in principle, I think it's QEMU is running directly on the hardware, or it's emulated.
I think well, there's probably some.
Okay, well, I don't know then.
But if you want we could start a Linux virtual machine and run it. That would be possible. Run that on QEMU and check. We probably have the old Ubuntu 6 machine that we could try that out.
This looks like the kind of thing the Tunes project would love to see, but it's, I think, defunct about 10 years now.
You mean the Tunes author is right back there?
Don't say
What?
that.
That's not
not
good.
Wonderful.
You're into it? Well, I want to say actually that I've been inspired by some of your writings.
Okay, thank
So,
you.
I mean, there's a bit of you in all of this, at least in the spirit of trying to do this.
Thank you.
Converted a lot.
That's not very durable.
Okay.
Looks like everything about Tunes is worthwhile except the schedule. It's still
So
coming
we'll
about.
have maybe one last talk before a break,
Yeah.
and then I think we're still okay. So maybe talk.
Sure.